Last day of 4.3, we are doing 4.3c, continuing with our trig. We are going to be doing trig for quite some time. It is a large unit, it's very important, and it includes so many elements. But let's continue. Let's work backwards this time. Okay, remember today, I want to remind you of our 30, 60, 90 and our 45, 45, 90. Remember, 1 to root 3 to 2 and 1 to 1 to root 2 or 1 root 2. Let's say we are given an angle, right? So let's say we are given the secant of theta equals 2, and we need to find what the degree is. Well, let's think about this, okay? So secant is hypotenuse is secant is the opposite of cosine, right? And cosine is ka, so it's secant then is hypotenuse over our adjacent. So with a secant of 2, I'm going to assume we can always put a 1 underneath the 2, okay? If our hypotenuse is 2 and our adjacent is 1, right? So then this would be our theta here, right? Because this is our hypotenuse here. This is our adjacent. And I know this is my 60-degree angle, because this is my 30. So this has to be 60, because from our 1 reflects back on the 30. So here, I know this has to be then 60 degrees. If I want that in radians, remember I need to divide by 180, multiply by pi, divide by 180. That gives me pi over 3 in radians. What if I was given, let's try another example of that, right? Let's say I was given sine of theta is root 2 over 2. Well, I know when I deal with root 2 and 2, I am dealing with my 45, 45, 90 degrees. And if I rewrote this with that root 2 and the denominator, right, then this would be the same thing as saying 1 divided by root 2. So my sine here and sine so it's opposite over hypotenuse. And this is always root 2. When this is 1 here, both of them are 1. So this could be theta. So I know theta has to be 45 degrees. If I want it in radians, I just got to divide by 180 times by pi. This gives me pi over 4 radians. Let's try another example. Let's say we are not doing our 45 degree angle per se, or we could be. Let's say we have 1 degree we know for sure. Let's say this is our 60 degrees right here. And I definitely know this is my 30 degrees. And this is 18. Well, remember our formula of this is x and this is x root 3 and this is 2x. Well, then x must equal, here in this case, 9. So this down here is 9. This is 9 root 3. If I needed to find the exact values of x and y here, right? If this was given like so, and this is x and this is y, well, then my x would equal 9 and my y would equal 9 root 3, or 9 comma 9 root 3, just like so. Lastly, we have to try to think of scenarios and how this could be done in real life. Okay, so if you were given an example, let's say a balloon. We got a weather balloon, and this balloon is at some random height. It's tacked to the ground. You're here holding your balloon. It's pretty windy out. And we'll say this balloon is initially, we'll say the string is 120 feet. And the initial degree of from the ground to the balloon is 35 degrees. If the degree increases, right, this gets bigger, then the balloon obviously must begin higher. If that balloon degree decreases, right, like that down here, it decreases, then obviously that balloon must be getting lower to the ground, as we think of it logically right there. If we need to find the exact amounts, like the height, say our original height here from that balloon, well, we know this is 35 degree. We just need to find x, the height. So we need something that is opposite over hypotenuse. So we can use sine. So the sine of 35 degrees must equal x over 120. Then to find x, then to find that height, we can say, 120 times sine of 35 will give us our actual height of the balloon. Put that into our calculator here. Sine of 35 times 120 gives me 68.83 feet, or 68.8 feet, like so.